So the direction I thought I was going to take the last video, and then it changed in the middle of it, was a discussion of how, uh, I mean, it sort of did this, how viewing infinite decimal expansions as basic hides the existence of things like L naught. Right? So, if you think that 1/3 is best represented as 0.3 repeating, how do you express that? I mean, how do you really express that? Because you can never finish writing it, right? What you do is you just kind of give up after a few digits, right? You might write it as like this, or are we doing 2 sig figs? Are we doing, right? Are we doing 6 sig figs? Right? What are we doing? And that, of course, plays into science and the precision of things and why they don't care that the mole was, when it was defined as a specific value, they just defined it as a rounded off. They just took what pretty much their central measurement was and just rounded it off at that point, instead of noticing that within their error bar there was only one available cube. There was only one cube within the space. So they should have just chosen that one, and then you could have a literal cube of matter, of one type of molecule or whatever, that is 1 mole. That would be really nice to be able to do. But no, because they're thinking this way, it didn't occur to them. Right? Because all they're looking at is decimal expansions. That's all that's important. Right? And that obfuscates all kinds of things. Like, what is 1/3 plus L naught? What is this? There isn't any other way to represent this value. Okay? This value is not 1/3. And you cannot, even if you could put down all of the infinite digits of the expansion, it would not look different from 1/3. Okay? L naught is so small that you cannot get to it this way. And this is why the Archimedean property doesn't apply here. Right? It's sort of a demonstration, and it's the explanation and the explanandum of that problem. The Archimedean property doesn't work here. You're never getting a 4, right, in the decimal expansion of this value. It's never, you know, it's not equal to 0 point, you know, like this. With more 3s, it just 3s forever, and then like 4. It never does that. It never does that. It's still always 3s. Its decimal expansion is still always going to be 3s. You're never, because what's happening with a decimal expansion, you're always dividing, right? You're always dividing. So you can think of 1/3 as, well, so it's 10 on 3, but we're taking the integer part of that. And then dividing that by 10, right? Plus, am I doing this right? I don't know. I'm just making this up on the spot, so I'm probably going to fuck it up. Anyway, the point is, like, you keep getting, so this is the 10th, 3/10ths, 300ths, yeah. Let's do it this way. Let's just do it this way. Right? That's what's happening, right? You keep having to add all of these fractions. You keep having all these divisions going on. The Archimedean property says there's always going to be another thing that you can do. There's always going to be another term to this, okay? And if we're approaching it this way, that's true. That's true. It's like trying to approach any value with a convergent series. That's exactly what this is, right? The series, the limit of the series is 1/3 in this case. This is absolutely true. However, it's never actually going to get there. So the series isn't the value. And how far off from the value is it? That doesn't make sense because it doesn't end, it's infinite. Right? So you get all of these problems with infinities, and then you get arguments like Cantor's diagonal argument trying to just obfuscate away the problems. And that's why it doesn't work. And it's also why, because he's looking at things this way, you're never able to see this. Because you can never even get here, let alone see the fine difference between here and here. That difference is so tiny, it's inaccessible to arithmetic. But we can see it. There's lots of places we can see it, and when we're taking limits of shit. But a really, really nice one that I keep showing is this one. Right? So the limit, as x approaches 0 from the positive, of 1 on x is one on L naught, or positive infinity. So the inverse of the inverse of L naught is infinity, positive infinity. If we take it from the negative, what this is this. So we get this. But then 1 on 0 itself is undefinable. And this is easily demonstrated via L'Hopital's rule. Among many, many other things demonstrate this. But L'Hopital's rule is a good thing to point to as a demonstration of this, because we know for sure that Leonhard Euler was aware of it, but he ignored it, because Leonhard Euler claimed that 1 on 0 was infinite. And many other people do. They follow his lead to this day. And if you look around on the internet, you will find people making that claim. Zach Starr is one that comes to mind. I know he made a video where he goes into this, talking about how 1 on 0 is infinite. He's wrong, right? The dude knows lots of stuff that I don't know, respect to him, but he's wrong on this. It's not true that 1 on 0 is infinite, and it's easily demonstrated. 1 on 0 is just meaningless gibberish on its own. Without context, it's nothing. You have to have a context to give it a value. So on its own, 1 on 0 is nothing. This is very similar to trying to argue that English uses an alphabet, right? Like, how do you pronounce this? People are going to be like, oh, well, obviously it's no. The K is silent. Well, but what about... Okay, here it's pronounced the way you're thinking. Here it's not. Here it's pronounced no. Right? Here it's no. Here it's no. Here it's kna. Right? The prefix is actually this. The prefix is actually a. This is introduced in order to make it more clear that we're actually pronouncing this now. But what is actually being pronounced is now kna. Acknowledge. So K-N-O-W in English does not have a pronunciation. The letters in the word don't tell you how to say it. In exactly the same way, this doesn't have a value. This operation, this alleged mathematical operation, 1 divided by 0, there's not enough information here to tell you how to evaluate it. You can't do that. So Euler's wrong on this count, for sure. Okay. And it's exactly the same as this. And English does this, right? This should be a really, really familiar thing, right? How do you pronounce this? Is it rebel or is it rebel? Depends how it's placed in a sentence. Is it a noun? In which case it's rebel. Is it a verb? In which case it's rebel. They're pronounced differently. Produce, right? There's lots of these. English does this systematically. It is part of the grammar of English. And as such, it is one of the reasons that English doesn't even have an alphabet. So whenever somebody comes around and is like, oh, I improved the alphabet, and they're like pushing some like phonetic writing system, they're not understanding how English writing works in the first place. This goes back to my other video that I just put up. You're told as a kid that English has an alphabet, so you believe that it does, even though you can see, when you look at it, that that's absolutely nonsense. You cannot sound out words in English reliably at all. In languages that genuinely have alphabets, you can. Even in French. I can read French decently well, just like it's, for the most part, pretty understandable. Even when I don't know what the hell I'm saying. Brand new words, I can read them because I understand how the French alphabet works. It's very strange, and it's certainly not as nice as maybe like the Spanish alphabet or even Russian, but it is alphabetic. Like, for instance, in French, there is no vowel in this. This is literally just right? And you can see this in like the fact that this as a word often just gets reduced to this, right? If there's a thing with a vowel that starts with a vowel that comes after this word, we just write it like this in French, right? Or you get names like this, where this is just Jacques. There's no k. Or words like this, ku. What's the vowel is this? It's oo. This is just k, 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 ku. That's it right there. Ku, ku, ku. That's why this word is pronounced that way. Ku. But yeah, again, if you talk to French-speaking people, they won't know this because it's not what they were taught. They were taught something else. They think that there's a vowel there because it's written with two vowels, two letters that are called vowels. So in their head, it's k, right? K. They're wrong. It's not. And you can demonstrate this easily by just having them pronounce things. You can give them words to pronounce, and you can show them. But they're not going to walk away remembering this, really. They're going to think that you're crazy if you try to show them this. Exactly the same thing is happening here, right? You think I'm crazy for showing you these things, because this isn't what people like Leonhard Euler believed. Right. But the reason is that we're too obsessed with these slightly wrong ways that we were taught, and it just becomes fossilized in your mind, and you can't see past it, right? So, like, this little thing here, L naught, which is just a shorthand for all of this bullshit, and if you want to restructure that any way you want, that's fine, but just understand what I'm pointing at here. It is something that has been invisible, something that has been ignored, and something which shows us that Cantor was wrong, Euler was wrong, even Gödel was wrong, Peano was definitely wrong, right? But there's some interesting nuance that's happening here now, because L naught is not subject to arithmetic in the same way. You cannot divide it. You cannot subdivide L naught. L naught is atomic. Okay? And this sort of vindicates Peano's axioms in a strange way, because L naught is now the proper successor to 0 in the way that Peano's successor function tries to make 1 the successor to 0. The problem is 1 can be subdivided, right? So you end up with paradoxes that arise because Peano's axioms establish a discretized number system, and then almost immediately, once you get to multiplication and you try to reverse that, you go into a continuous number system, and you get all kinds of crazy shit happening, and this yields in pretty much immediately, this is what gives you the incompleteness theorems, right? Because now, if you're not understanding what's going on here, if you're not careful enough to see this, you're going to think, well, we can just apply a diagonal argument like Cantor did, and we can just find these things that give us a proof by contradiction, and therefore we don't get completeness. And I'm not saying that completeness is all that important. What I'm saying is this is pointing to a problem with the fundamental arguments, the axioms of the whole system. Here, L naught is atomic. It cannot be subdivided. So it is the truest possible successor to 0. Okay? It cannot be subdivided. But also at the same time, it's operating like Cantor's transfinites, because in order to grow this out big enough that you can even see it with arithmetic, you can't do that with arithmetic, right? You can't grow it out big enough to see it with arithmetic, right? You can't get this. Let's say, let's do this. Right, so this is just, a third. Right. There is no value of n that can do this. Okay. Now you're thinking, well, okay, what if we just do exponents? There's no value of n that can do this either. There's no way to, right, and say we use the up arrow notation, right? So, I don't have that symbol. Whatever. Boom, boom, and doesn't matter. You can't get it there. You can't get it there via arithmetic or any extension of arithmetic. You can't do this. And that's also why you can't use arithmetic to get down to it, right? It doesn't work either way, right? You're never going to get it this big. You're never going to move 1/3 that much using any multiple of this. So this is atomic, it is discrete, it is the proper successor to 0, and it does absolutely exist. But arithmetic, algebra, for the most part, is the wrong tool to be using to try to get at it from larger values. You can't do that. The only way really to do it is to take whatever value you're interested in and look at the space right next to it. Okay, and this is on a scale far smaller than infinitesimals or monads or whatever. This is at a scale that Cantor can't see, because his normal forms, they're working with transfinites. His, like, all of this stuff, like Aleph naught, Aleph 1, all that stuff, which personally I think all collapses into a single thing at this point. At this point, that's what I believe now. Aleph naught is Aleph1, is Aleph2, is Aleph3, right? That entire infinitude, they're the same thing. They collapse into one thing, if you understand this correctly. And that actually resolves a lot of paradoxes. That's a good result, actually. But yeah, you can't get there with those things, because those are arithmetic manipulations. You cannot use arithmetic to manipulate your way down to this. But we have tools for this. Limits. We know how to take limits. We know how to look at limits. Limits literally give us this exact tool. And they were known to Euler. He was able to do this because calculus had been invented already before he came around. It was yeah, I mean, it's not a coincidence that Johann Bernoulli was one of the prominent figures in the development of the calculus. It was newly invented at that time. Right? There hadn't really been much opportunity for someone earlier, and Johann Bernoulli was just in the right position, with the right skill set, at the right time, at the right moment. This is when it was developed. He was, he communicated with Gottfried Leibniz, right? It's that period of time. Limits are known. Sure, there's, not as well known as today. Sure, that's fine, because knowledge grows. But this was knowable at that time. But I think because of their entrenchment with certain ways of thinking about things, it wasn't noticed at least not very clearly, not in a clearly communicable way. So anyone who did notice it, it didn't get passed on. It didn't become part of the culture of mathematics. And now here we are. We're at this weird stage where you get lots of just like overconfidence in these results. It's really strange to me that Georg Cantor would be so excited about this to try to produce proofs when really he's not saying anything different than Galileo's paradox. Right? His diagonal argument is not actually different than Galileo's paradox. It's just more specifically formulated in a set theoretic way, but you could very easily just take Galileo's paradox directly and frame it in a set theoretic way. Like, why do you have to do this extra work? Why are we showing off? What is this? That's unnecessary.